stopped in the last class. So
Yes,
we're
sir.
talking about the quantum numbers. So we talked about the four major quantum numbers and their significance. So the principal quantum number, the azimuthal quantum number, magnetic quantum number, and spin quantum number. So we talked about their significance. So today we'll continue in.
Yes.
Yes, sir.
So what is isotopy? That's the question. Anybody? Anybody?
Isotopy can be
Okay.
defined as the behavior of atoms to have same atomic number and different mass number.
God bless you. Those are for you. So it's a behavior or a phenomenon that is exhibited by certain atoms. By certain atoms, right? Possessing possessing same atomic number, same atomic number, but different mass number. Does that make sense?
Yes, sir.
Good. Now, for example, if you have e.g., you have chlorine. Chlorine exists in two isotopic form. You have chlorine 1735 and then you have chlorine 1737. Are we there? Now in this
Yes,
case,
sir.
Yes, sir.
chlorine has the same atomic number 1717. So atomic number is the same, but the mass number is different. Mass number is different. That's 35 and 37. So what makes the mass number different is actually the number of neutrons. So because number of neutrons here is going to be different. So to get the number of neutrons, what are we going to do for the first isotope? Right, so let's assume isotope 1. The number of neutrons is 35 minus 17. So the number of neutrons will be what? That's 18, right? The second one,
Yes, sir.
isotope 2, the number of neutrons will be 37 minus 17, and that will be what? 20. So you can see what makes this different is actually the number of neutrons. So chlorine, for example, is an atom exhibiting isotopy with the same atomic number but different mass number due to the difference in the number of neutrons. So apart from that, we have some other elements that exhibit isotopy. So we can talk about elements like hydrogen. Are you together? I will give you some of their what's it called isotopy. We have carbon also, right? We've mentioned chlorine. We have oxygen, etc. Several elements undergo what? Isotopy. But the ones that are very prevalent that we are supposed to know and their behavior are the following: hydrogen, the isotopic behavior of hydrogen. Are we listening? So,
Yes, sir.
hydrogen has three major isotopes. What are they? You have H11, you have H12, and then you have H13. These are the three isotopes of hydrogen. The first one, H11, is called protium. This one, H12, is called deuterium. And H13 is called the tritium. So we know that H11 has no neutrons. No neutron. It has no neutron because if you subtract the mass number from atomic number from the mass number, so deuterium. Deuterium is also known as heavy hydrogen. Heavy hydrogen. Then you have the tritium, which is radioactive. It's a radioactive isotope. So one of the things you must know about these um, three isotopes are the following I've said. Apart from hydrogen, another important isotope you need to know about is carbon. Okay, so for carbon, the three major isotopes are carbon 612. Are you listening? Carbon 613 and carbon 614. These are the three major isotopes that we have for carbon. Now, this carbon 612 is majorly used to detect or to determine atomic number, right, and relative abundance of atoms. So you want to know the relative abundance of atom. Okay, what is the fraction of the percentage or the fraction of some isotopic mixture? You can use this carbon 612. Carbon 613 is majorly used for monitoring reaction, metabolic reaction, for monitoring metabolic reaction. Right, so it's like a tracer. If you want to monitor reactions in the body, for example, you can use carbon 613. I hope you are listening. Then carbon 614 is for archaeological dating. They use it a lot in detecting the ages of old fossil records, archaeological dating. So sometimes you'll be hearing things like this rock has existed for about 500,000 years ago. They use archaeological dating for that purpose. And what element is actually used for that is carbon 614 for archaeological purposes. Is that okay? Is that understood?
Yes, sir.
Then apart from that, another important chemical that is used for this process, for this reaction, apart from the fact that carbon 614 is used for archaeological dating, it's also very important. It's also radioactive. So if you are asked which of the isotope is radioactive, you know it is carbon radioactive. Okay, is that understood? Is that understood? Now, so those are the common isotopes that we have for hydrogen and carbon, and we are supposed to know what they are actually used for. So now you get to realize that in the periodic table, most of the elements existing, if you check a periodic table, you get to realize that most of the elements existing are not in a whole number. So you always see them in decimals. Let me give you an example. Let's see. For example, if you look at periodic table, you see the mass number of hydrogen is always 1.01 something. Chlorine, for example, the mass number is around 35.5. Are you getting my point? You always see them in decimals. In decimals. You don't see them mostly in whole numbers. This is simply because of what? Isotopy. Am I communicating? Hello? Now, the reason why most of the elements in the periodic table are existing in fractions or in decimals is simply because of what? Isotopy. Because most of these elements exist in isotopic mixtures. For example, if you look at hydrogen, like we said, hydrogen exists in isotopic mixture. You have H11, are we there? H12 and H13. Am I communicating? Now all these now, they need to be represented in the periodic table. Am I talking?
Yes, sir.
So to represent hydrogen in the periodic table, then you must get the average of the whole of these isotopes. So each of them are present in this hydrogen in different fractions or abundance. So the abundance of their existence is what we call relative abundance, right? So the relative abundance is what? The fraction of isotopic mixture. The fraction of isotopic mixture. Are you listening?
Yes, sir.
Yes,
Present,
sir.
yes, present in an atom. So every atom, for example, is not made up of just one type of isotope. Most of them have at least two isotopes making them up. So each of those isotopes are present in a particular fraction. So that fraction of existence is what we call relative abundance. Is that okay? Now, the instrument we use in actually measuring this relative abundance of isotope is called the spectrometer, right? We have what we call the mass spectrometer. Mass spectrometer. So the mass spectrometer is an instrument that is used in detecting the atomic mass of a given atom and its relative abundance. Atomic mass and what? Relative abundance. Is that okay? The instrument is called what?
Yes, sir.
Mass spectrometer. I hope you guys are noting what I'm doing. Calculation on isotopy. Okay, so let's look at the calculation on isotopy. So now, just like I said, in calculating isotopy, we have a number of formulas that are used. So the basic one is relative atomic mass, RAM, is equal to summation Mi alpha I. Is that okay? So where Mi represents the mass number. Am I talking?
Yes, sir.
Yes, sir.
And alpha I represents relative abundance. Alpha I represents what? Relative abundance. Now, this relative abundance can be given in percentages or in fractions. So we'll look at that later. But for now, if you are given two isotopes, for example, if you are dealing with two isotopes, if you are dealing with two isotopes, so the relative atomic mass will be equals to m1 alpha 1 plus what? m2 alpha 2. If you are dealing with three isotopes, am I talking?
Yes,
Yes.
sir.
The relative atomic mass will be equals to m1 alpha 1 plus m2 alpha 2 plus m3 alpha 3. If you are dealing with four isotopes, relative abundance will be equals to m1 alpha 1 plus m2 alpha 2 plus m3 alpha 3 plus m4 alpha 4. Is that okay? So depending on the number of isotopes. Now note, sometimes the relative abundance, just like I said, relative abundance can be given in percentage. So in percentage, this implies that, right, the summation of all the relative abundances must be equal to 100%. So if in case I was given alpha 1 to be equals to 60%, right, I definitely know that alpha 2 will be what? 100% minus 60%, which will give me what? 40%, right? This is 2
Yes, sir.
good. So if I have other things like that, so you should know that the summation of all of them is 100%. But if it is in fraction, you should know that the whole of alpha 1 plus alpha 2 plus blah 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 must be equals to 1. So for 2, for example, if I have alpha 1 equals to 1 over 3, so it implies that my alpha 2 without me being given will be equals to 1 minus 1 over 3, which will give me what? 2 over 3. Does that make sense?
Yes, sir.
Now, if I'm given it in ratio, for example, they say it is 1 ratio 3, the ratio of existence. So it means that my alpha 1 is equal to 1. Alpha 1 equals to 1 over 1 plus 3, which is equal to 1 over 4, right? And my alpha 2 will be equals to 3 over 1 plus 3, which will be equals to 3 over 4. Is that understood? Is that
Yes, sir.
understood?
Yes, sir.
Okay, let us look
Yes,
at
sir.
some examples. Give me a few seconds. Let me put this. So let us look at some examples quickly. So that we can leave that part on time so that we can address some other things. So if you are given a question like this, I don't know, but let me quickly get this question like this. If that this compound has mass number here, this is the first isotope and this is the second isotope. So my M1, that is the atomic mass of isotope 1, is 35, and M2 is 37. Is that clear?
Yes, sir.
So you can see here that this is 75 for the first relative abundance. Alpha 1 is 75%, and my alpha 2 will be what? 25%. So with that, we can quickly estimate the relative atomic mass, RAM. That would definitely be equals to M1, since you have two isotopes only, alpha 1 plus M2 alpha 2.
Alpha.
So the relative atomic mass will be equals to 35 multiplied by alpha 1, which is 75 over 100, plus M2, which is 37, times alpha 2, that's 25 over 100. So when you do the calculation, we'll be having 35.5. So that's our relative atomic mass. Does that make sense?
Yes, sir.
It means for this, the atomic masses for the first one is 6 and the second is 7. So my M1 will be equals to 6 and my M2 will be equals to 7. So alpha 1 will be equals to 3 over 2 plus 3, which is equal to 3, which is, 3 over 5. My alpha 2 will be equals to 2 over 2 plus 3, which is equal to 2 over 5, right? So the relative atomic mass will be equal to, since there are two isotopes, M1 alpha 1 plus M2 alpha 2, which will give us M1 is 6, alpha 1 is 3 over 5, plus M2 is 7, alpha 2 is 2 over 5. So this will then give us what? So you can calculate that. This will give us 18 over 5 plus 14 over 5. So that will give us 18 plus 14, that will give us 32 over 5. So what is 32 over 5, ladies and gentlemen?
6.4.
So the answer is 6.4 as the relative atomic mass. I hope that's understood. So you should know how to apply
Yes, sir.
fractions when the relative abundance is in fraction, meaning in ratio form, and when it is in decimal form. Calculation of molar masses and percentage abundance. So if I have something like C6H6 and I'm told to calculate the molar masses of C6H6, NaCl, right, CuSO4.5H2O. Let me start with this quickly. So I'll be given the atomic mass for carbon, hydrogen, sodium, chlorine,
And
copper, sulfur, hydrogen, oxygen, 16. So if I want to calculate the molar mass, so the first one, which is C6H6, which is benzene, that one will be 12 multiplied by 6. Are we there? Plus hydrogen is 1 times 6. So let's sum it together. This will give me 76 plus 6, and that will give me 82. Are we together? Sorry, L.
Yes, sir.
72, not 76. 2 seconds, please. That is 72 plus 6, that will be 78. Now, since it is molar mass, that will be gram per mole. Unit of molar mass is gram per mole. But if they say relative molecular mass, there won't be what? Units. Anything relative, if it is RMM, there is no units. But if it is molar mass, unit is gram per mole. Let's take note of that. So if you are taking the second one is ACl. So this will be 23 plus 35.5, which will give us what? 58.5 gram per mole. So the third one is CuSO4.5H2O. For this, we'll be having 64 plus 32 plus 16 times 4 plus 5 into bracket. You can see this, we have H2O. That's 1 times 2 plus 16. So then I can add them up together. 64 plus 32 plus, this is 16 times 4, that's 64, right? Plus 5 into bracket, 18. I hope you are following. So this 2 plus this is 6. This plus this is 9 plus 64 plus 5 times 18. 5 times 8 is 40. 40. This is 5. This is 90. I hope you are listening. This plus this, that is 0. This plus this, that's 16. Are we together? Plus 90. Can you hear me? So this is going to be what?
yes,
This
sir.
plus this, that is 5. And this is 2. I hope I'm correct. Sorry. 2. 9 plus 6. That's 15 now. How
15.
come
Yes.
correct?
Yes, sir.
So that's it. So that would be gram per mole. So now if you are told to calculate the percentage abundance, for example, if you are to calculate the percentage abundance of chlorine here, that would be the mass of chlorine over NaCl times 100%. Are we together? So chlorine there is 35.5 over the whole of it, that's 58.5, everything times 100%. Please, are you getting what I'm explaining?
Yes, sir.
So whatever you get is going to be what? Tell me your answer.
60.68.
60.7.
60.68, approximately 60.70. Okay, fine. That's percentage in percent. Okay, good. So let's calculate the molar mass first. So percentage of oxygen is, how many oxygen do you have? Two oxygen. You have two what? Oxygen. Are you following? Over CH3 COOH times 100%, right? So that will give us, the atomic mass of oxygen is 16. So we multiply by 16 over the whole of methane, which ethanoic acid, which is CH3 COOH. Let's calculate that. That will give us 12 for carbon plus
48.
1 times 3 plus
48.
48. Agreed by everybody? 48 times 100. So this is going to give us 32. Are you listening? Is it 48 or you
Yes,
want me
sir.
to do it? Or is not 48?
It's 60.
Yes, sir.
60.
60.
60.
Yes.
Okay. Mama, why are you calling 48? It's 60.
So for my answer, I got 56 points. I said 53.28.
Don't worry, we are going to confirm that now. So this is 12, right? Plus 3, that's 15. Plus, this is another 12. So plus 16, 16, that's 32. Plus 1. So let's add them together. 15 plus 12, that is 27. 27 plus
Yes.
33, that's 60. So this is
60.
60.
Yes.
So this is going to be 32, since it is oxygen,
Thank
divided by 60
you.
times 100%. So what is the answer?
So
Definitely
my
you
answer
can.
is 53.
53.8%. So
Theory.
that's
Theory.
23, right? Is that what you got to, Olamide?
Yes, sir.
So
53.28.
Dean, did you see where your mistake is?
Yes, sir.
Okay, fine. So we can move to the next task. Now the next thing we want to discuss now is empirical formula and molecular formula. So what do you mean by empirical formula and molecular? Empirical formula is a formula that shows the simplest ratio of existence of atom in a given molecule or compound, right, is making up a molecule. For example, if I have benzene, benzene is an organic compound with formula C6H6. So the empirical formula of benzene, showing the simplest ratio, empirical formula will be C6 ratio what? Let me read it this way. I hope you can see what I'm doing.
Yes, sir. Yes,
You
sir.
have C
Yes,
and
sir.
then you have hydrogen. So since I have 6 carbon and 6 hydrogen, So divide it by 6 and by 6. So they can be 1:1. So it means C1H1. So it means the empirical formula, the simplest ratio of existence of benzene is C1H1, which is the same thing as CH.
Come again. Come again.
Now this
I don't understand.
the benzene here, right, is having a molecular formula of C6, isn't it? So that means 6 carbon atom and 6 hydrogen atom making up that compound, isn't it? Are we together?
Yes,
Yes,
sir.
Yes,
sir.
sir.
Now, we are now saying that since they exist in ratio 6 to 6, 6:6, so it implies that they can divide one another, which is equivalent to what? 6/6. The 1 here, 1 here. So it's same thing as 1:1. So that 6:6 is like C1H1. So it's like CH. So the simplest form of ratio of existence is what? CH for benzene. So we can say the empirical formula of benzene, which is C6H6, is what? CH. Is that okay?
Yes, sir.
Yes, sir.
Now let me give you more examples so that I can get it better. Now let's assume you have another one, like would be, since it is 6:12:6, 6 can go in all of them. 6 here 1, 6 here 2,
One ratio
6
two
here 1.
ratio one.
God bless you. So the empirical formula of glucose would be equals to C1H2O1, which is the same thing as what? CH2O. So that's the empirical formula of glucose. Does that make sense?
Yes, sir.
Okay. So if I have a compound like this, C, okay, let me take N2O4. What will be the empirical formula, please?
NO2.
Thank you. NO2, which is N1O2. That will be the empirical formula. So empirical formula always tells us the what? Ratio of existence. The simplest ratio of existence, right? So then we have, so molecular formula is a formula that shows the actual number of what? Of atoms present in a given molecule or what? Compound. So what molecular formula does is just gives us the actual, what's it called? So just like we said, benzene, what is the actual formula? That is C6H6. So this is the molecular formula. Glucose, what is the actual formula? C6H12O6. That is the molecular formula. Is that clear?
Yes, sir.
Yes, sir.
Again, C10H22. That's the molecular formula. And so on and so forth. So however, there is now some relationship and some calculations under this aspect, so we need to know them. There is another one, structural formula, but it's not needed now. So when we discuss, multiplied by N equals to molar mass. That's one of the formula. I hope you guys are writing.
Yes, sir. This
Yeah,
formula is for what?
we use
Yes, sir.
it. There are formulas that we use in calculation, or empirical formula and molecular formula. So another one is 2 times vapor density equals to molar mass. That's equation 2. And there is another one that says that empirical formula multiplied by n again is equal to what, or gives us molecular formula. This is equation number 3. So let's look at how to resolve these problems. So when you have questions involving this stuff, so how do we deal with them and how do we solve the questions? So I'll pick like few questions and then we'll look at it. Okay, can I proceed? I'm trying to
Yes, sir. Yes,
check
sir.
questions. So let me pick few questions here. Now, I want to calculate the empirical formula. So what we do normally when you are calculating empirical formula is to divide them into 3 parts. You have sodium. Are you listening?
Yes, sir.
We have carbon and then you have oxygen. So the first one is 43.4. The next one is what? 11.3. And the next one is 45.3, I guess. So the first thing we do is to divide each of the masses given, right? Each of the percentage given, to convert them to mole. So to convert it to mole, we will do mass over molar mass. So we are dividing each of them by the atomic masses. So the atomic mass of sodium here is 23. So I have this divided by 23. Are you following? This divided by 12 and this divided by 16. Does that make sense?
Yes, sir.
So
Yes, sir.
43.3 divided by 23 will give me 1.89. And that will give me what? 0.9. You confirm, please. And this will give me 2.83. Is that okay? Now the next thing I do is to divide by the smallest decimal. The smallest decimal there is 0.94. So I'm going to have, which is for Na, carbon and oxygen. So I divide this by the smallest number, 0.94, and this is 0.94 divided by 0.94, and lastly 2.83 divided by 0.94. So let's divide that. This will give us 2.01. This will give us 1.00, and this will give us 3.04. So in the end, what we are getting here is 2:1:3. Does that make sense? So it means the
Yes, sir.
empirical formula of the compound will be Na1 Na2 C1O3, which is equivalent to Na2CO3. Do you get that?
Yes,
Yes,
sir.
sir.
So that is how to quickly calculate that. Now sometimes there are some things you don't just approximate. Like these ones now, you approximate them easily. You approximate this one easily. But there are some values that are not expected to be approximated directly. So you are going to divide it into the portions carbon and hydrogen, since it is a hydrocarbon. Hydrocarbon is made up of carbon and hydrogen. So we are only given the percentage of carbon, which is 80%. Are you listening? So it means that of hydrogen will be 20. Though you are not given, but we should know that since hydrocarbon is made up of hydrogen and carbon was only 20, it means hydrogen will be, carbon is 80, it means hydrogen will be 20. Is that understood?
Yes, sir.
So you divide
Yes,
this by
sir.
12 and divide this by 1. So this will give you what? So 80 divided by 12 gives you what? Are you working there? I think that should be 6.67.
6.6.
And this will give us 20. Divide by the smallest number, which is 6.67. 6.67. So that will give us carbon here, hydrogen. This will give us 1, and that will give us 3, right?
2.3.
Are we there? Are we there?
Yes.
So this
Yes,
one
sir.
is actually straightforward. So the empirical formula here is CH3. Now the question is not to get empirical formula. The question is to get the molecular formula. So how do you relate molecular formula to empirical formula? Times N equals to what? Molar mass. Are we together? So the
Yes, sir.
empirical formula was CH3. We've calculated CH3 into bracket N equals to the molar mass. The molar mass in the question is what? Look at it again. That's 30. So relative molecular mass of 30. Sorry. So it means the molar mass is 30. So this is going to be 30. Are we together? So this implies that 12, atomic mass of carbon is 12, plus atomic mass of hydrogen is 1 times 3. Are you listening? Everything multiplied by n is equal to 30. So you are trying to look for the value of n now. So this will give us 12 plus 3 into the bracket n equals to 30. So that will give us 15n equals to 30. Therefore, n equals to 30 over what? 15. N equals to 2. Are we together? Then put the value into the empirical formula. So we have molecular formula, right, is equal to what? Empirical formula multiplied by what? N. So the empirical formula is CH3 multiplied by the value of N, which is 2. So now use that value to multiply what is inside. That will give us C2H6. So this is the molecular formula. Does that make sense?
Yes, sir.
Yes.
Mm.
So